Hello. Hey, thanks for having me on. I'm excited to speak to you and also to our audience today. I do really encourage you to ask questions during this presentation, but really what I'd like to get into is talking about how DTrace and Python interact and why DTrace is a really powerful tool that you should add to your toolkit when you're using other tools to profile your code and to debug really tricky problems that you may not otherwise have any kind of visibility into. So the first thing I really wanted to talk about were basics about DTrace. I know that it's a technology that's been around for a long time. It was invented at Sun Microsystems in 2005, and it was one of the first open source projects that Sun released into the wild, and it lives on today in all of the child projects of Open Solaris. We'll get into what supported operating systems there are later in this talk. But really, the talk has four basic parts. Part one is covering the basics about DTrace, what it is, why it's useful, what are the capabilities of the technology. Part two is talking about the terminology. DTrace has kind of a specific lingo, and so I wanted to gloss some of the common terms that are used by the DTrace community so that when people ask questions about providers or consumers, they'll know what they're talking about. The third part is really digging into the D script language. So DTrace has a very awk or C-like scripting language, and we're going to talk about the basics of the syntax and how to apply it to Python specifically today. I should point out that DTrace facilities are usually available in almost every popular programming language out there: PHP, Perl, Ruby, JavaScript, Python, of course. And at OSCON, I'll be discussing how DTrace and Erlang work together because I do a lot of Erlang in my day job now. So that's something I've been digging into for a while. Without further ado, I'm going to go ahead and get started here. The first question that people always ask me is, what is DTrace? So that's a really important question to ask, and the answer to that is that it stands for dynamic tracing. And I realize that that term doesn't necessarily mean a lot of things to people. So it's kind of like, what is it dynamic against? Well, most of us have written code something similar to this. For example, when you're tracing through code pathways, maybe you'll put like little markers into it, like I got here, or I was able to reach this code path, or if you're debugging if-else logic, I took option 1 or I took option 2, that sort of thing. And then there's also the app profile, so you can decorate a function with a profiler, and it will give you detailed statistics about how long it took to execute. Of course, people roll their own profiling technology where they'll take a timestamp when the function starts, and they'll take a timestamp when the function includes, and they'll take the difference of that and spit it out to standard out or put it into a log file or something like that. By the way, this decorator that I've put into my slide here, the URL of this is at the bottom of the slide, is actually a really good complementary technology for DTrace. And it's something that I think is a really neat project. If you are at all interested in doing performance profiling in Python in a really, quote, Pythonic way, this is a great project for you to check out. So what DTrace really is an observability technology. And what that means is that the idea is that you want to be able to see all of the parts of your operating system, everything from your application code down into the libraries that it's calling, down into the system level calls, so the calls that those libraries are making to the operating system, and then actually what the kernel itself is doing. DTrace, even at some levels, can show you indirectly what the hardware level of your operating system is doing, which is pretty cool. So it gives you a lot of insight into what the actual behavior of your computer is. You don't have to guess anymore. You don't have to make suppositions. You can actually find out once and for all with DTrace what the code path is and what parts of that code path are taking the longest amounts of time. So it's a great tool to show you all of the different parts of your operating system working together to provide the application functionality that your application is supposed to implement. On a DTrace-enabled operating system, you get full scope. And what I mean by that is really this. So you mentioned this before, but it's really focused on you have your application, it goes to the libraries, goes to the system calls, goes to the kernel, and then it goes all the way back up that stack too. One of the things that DTrace is really good at is being able to zero in on each one of those 4 different components and help you isolate the specific performance of all of those different components and subsystems when they're working in concert. So while your application is running in a typical environment, you can fire up DTrace and actually use the tools that DTrace provides to you to determine a great deal of information that otherwise would not be visible to you. One of the things that people ask me frequently is, why would I choose to use DTrace rather than a profiler? Because, I understand what profiling is, and there's really rich profiling tools that are available for Python. Why don't you just stick with profiling? And the answer to that question, I think, has 2 components. The first part is that I don't think that profiling and DTrace are opposites. I don't think that they're things that compete with one another. I think that they're really complementary to one another. So on one hand, a profiler gives you really good and rich metadata about the performance of a particular pathway in your code. And on the other hand, DTrace really gives you the visibility into this full stack that I have on my slide, all the way down and all the way back up. So, within a specific number that a profiler might give you, you often wonder, well, which part of this is taking the longest amount of time? Am I waiting on, for example, if I have rotational disk, am I waiting on disk rotation? Am I waiting on a memory event? Is there a mutex that's being held somewhere that's interfering with that's creating sockets or something like that? So this is a really great technology to use in conjunction with profiling. And when you find a hotspot or you find a trouble area in your application code, that would be a great time to get DTrace out of the toolkit and start really digging into what is causing the slowdown or what is causing that problem within your code base. So one of the things that DTrace really shows you is that it's turtles all the way down. And what that means is it's a reference to a story, which I will quickly tell you. And the story is that there was a woman who was at a conference, and she was asking questions of the speaker, and he was explaining that the Earth revolved around the sun, and she said, no, it's actually the Earth travels in the back of a turtle. And the lecturer said, well, what's underneath the turtle? And she said, you're not going to trick me. It's actually another turtle. And he said, well, what's underneath that turtle? And she said, well, it's actually turtles all the way down. And so what DTrace shows you is that you have turtles all the way down, and it lets you see every single one of those turtles. It's like X-ray vision. It's neckbeardy. It's fun. It's good stuff. Some examples of things that DTrace would be really good at helping you diagnose, for example, is you could trace when socket access happen in your web application, and you'd be able to do that during real live code execution without writing any sort of instrumentation code. So you would essentially deploy the DTrace probes, you would execute your web application or whatever it was, and you'd be able to see as DTrace collects that information, what is the actual code pathway through there. Another thing that DTrace would be really good at is trying to profile why your shared file service gets really busy at some specific time, and instead of traversing a tree through that in 2 minutes, it takes 2 hours. What is causing that? Why does that happen? As I mentioned at the top of the hour, DTrace is only available on specific operating systems, and those are Solaris 10 and up, so Solaris 10 and 11, the Open Solaris, and Illumos. Illumos is like a fork of Open Solaris, and then Illumos kind of has some child projects. One's called Smart OS from Joyent, and the other is called OmniOS from OmniTI. And then I think around 2007 or 2008, FreeBSD ported DTrace to its stack, and so it's been around in FreeBSD for a while now. And then in Mac OS 10.7, Apple ported DTrace into Mac OS 10. So if you're watching this session on a Macintosh today and you're running OS 10.7 or higher, then you actually have DTrace built into your operating system right now. And it's totally available for you to use and play with. There is a caveat to that, which is that unfortunately the Python that comes out of the box with OS 10 is not DTrace enabled, but we're going to cover how to get the DTrace enabled Python later in this talk. Another really common question that people ask me is, what about Linux? Unfortunately, there's been, I don't know really delicately how to put this, there's been a lot of licensing controversy. Sun released the DTrace technology under their common license, which was not GPL compatible, and so there was a lot of consternation in the Linux community about taking up this code base, which they felt had an incompatible license, and so there was a lot of hesitation to do this. I have since discovered that there is a kernel module which is maintained separately from the Linux kernel, which provides a lot of the DTrace functionality, but I have never used it myself, so I can't actually speak to its utility or if it's actually correct or not, but it seems to be good stuff. I'm definitely interested in testing it. I just haven't been able to get around to it yet. So unfortunately, for today's talk, if you're looking for Linux, you're pretty much looking for the talk called System Tap Python and you might want to try that in the hall. It's on the left side. The next thing I wanted to cover was DTrace terms. And since we're going to switch topics here, I thought it would be a good time to see if there's any questions from folks. So I'm going to check the tab here real quick. Audra or Yasmina, did you see any specific questions that look good?
Yes, actually. We have a question here. Where can I get DTrace?
Right. So if you have a DTrace supported operating system, you don't have to do anything special. You just get it for free. If you have Linux, then there is a GitHub project, which I said has a kernel module. It provides a lot of the DTrace functionality. In fact, I believe it passes all of the DTrace spec tests, but as I said, I haven't personally used it, so I can't speak to its utility or if it's actually correct. It's definitely something that I want to play with, but I haven't been able to do that yet. That is a great question, and I do have some URLs that I want to share at the end of the talk, and I'll see if I can look up the DTrace modules for Linux at the end of the talk, and I'll just put it in the chat window, and hopefully we'll pick that up. So as I mentioned at the top of the talk, we're going to talk about the terms, and just real quick, we'll go over several of the terms that people use when they're talking about DTrace, and specifically DTrace in the context of how it's implemented. So these are implementation terms, and they're kind of a little bit confusing at first, but we're just going to roll through them and hopefully explain them. So the first term is a provider, and what you'll hear today is that Python itself is a DTrace provider, and what that means is that it manages probes in a subsystem. In this case, the subsystem is your application code, and a probe is essentially a tiny little unit of observability. So if there's a specific thing that you're trying to detect, if it happens, for example, let's say that the event is you want to know every time Python enters a new function, then that would be a probe, and Python is the provider of that probe. So the provider means this is a piece of software that gives you a unit of observability, which is called a probe, and this is what manages it. It is responsible for deploying the probe and relaying the information to the DTrace part of the kernel. And those two things work together. So DTrace sits inside the kernel space in your computer, in your operating system, and it talks to the DTrace provider. The DTrace provider provides to the kernel extension all of the various pieces of metadata about that event and collects them. And DTrace has all kinds of different functionality for collecting information, analyzing information, tabulating information. We're going to get into all of those different functions really soon. But the key thing here is that a provider is essentially a tool that provides DTrace functionality to the kernel, which is where DTrace sits. We covered this already, and we talked about how probes are observables. So they're a piece of instrumentation. And again, you think about this as an event. So this is an event that you're interested in. In the context of Python, for example, we use the function entry event. There's also a function exit event. There's a whole bunch of other events. We're going to talk about all the different probes that are available for Python. There are also a lot of other probes that are available from other parts of your system. For example, the socket library has a whole bunch of different events related to socket construction and deconstruction. There's a whole bunch of I/O probes that are available. For example, every time the operating system opens a file and provides a file handle, you can probe that. An event will fire. And then finally, there's another terminology piece here called a consumer. And essentially what a consumer is something that takes all of the DTrace information from the kernel where DTrace sits, and it's actually telling DTrace what you should do with that. So it informs the kernel what probes you care about, what it should do with the metadata that comes from those different probes event firing, how to tabulate that information, when that information should be tabulated, what format the information should be tabulated in. For example, should I print it the standard out right now, or should I just wait till the entire script is executed and print it at the end? So there's a bunch of different options that you have, and those are all coming down to the way that D itself works with DTrace. So the next little part of this talk is about language basics. So we're going to talk about language basics with DTrace and all the various pieces of functionality. We're not going to go too in-depth on this, unfortunately, but just know that DTrace is, the D scripting language is a really rich programming environment that provides a lot of functionality to you out of the box that you can just get for free. So if you're comfortable with awk, or you're comfortable with a C programming type language, you're going to be pretty comfortable with the D constructs. D itself feels very awk-like to me. You define a probe and an optional predicate, and then an optional action. The action sits inside of a braced clause, so it really does look a lot like awk to me, especially as one-liners. It supports begin and end blocks just like awk does, and it also supports some local variables. And those local variables can be arbitrarily named, and they can have arbitrary values. So, for example, here in this particular slide, I have this arrow foo equals 42, which means I'm setting the local variable foo to the value 42. It could have been a string. It could have been any arbitrary value that I care about. And the reason that that's useful is you can do things like record timestamps. You can do things like set truth condition. Those are all things that help you build really intelligent and sophisticated D scripts that let you do really sophisticated analysis of your code pathways. D also supports like 12 different aggregation functions. So it supports aggregated and associative variables. What I mean here is that it supports increments, and counters, and associative arrays, and all the things that you would expect to have in kind of a fairly modern programming language. I mean, D is not like a Turing complete programming language, but it's pretty good for what you get. And it also has one-liner support. The way you do that is you DTrace -n, and you specify the probe and a predicate and an action. You have those things. It's pretty straightforward. So here's our first DTrace example. This is completely contrived. This actually does not compile. There is no probe named probe. There's no predicate named predicate, and there's no action called action. But this is just to give you a flavor of what a DTrace script might look like if you happen to cat it from your command line. It would be something like this in the form of DTrace -s, which means all of the probes that follow -s, I want you to activate in the kernel. The predicate, like I talked about, which may or may not be present, and then there's actions. So, if probe fires, then increment counter. If the stamp is now, that's basically what I'm trying to So now what I'm going to do is actually show some example code, and hopefully this will make things a lot clearer. So this is your first real example. There we go. Had a little bit of slide lag there. I guess I got a little carried away with my forward button. So you can see here in this particular slide that function entry and function return are highlighted with yellow. With orange. And what those do are every time Python enters and returns from a function, it causes the braced clause here to execute. So every time a function is entered or returned in a Python application, the action that takes place there is this one, trace, copy, and stir arg1. So in this particular case, the function entry and function return, the arg, I should back up here and say that DTrace metadata starts with 0-based arrays, just like C does. And so arg1 is actually the second argument that these probes provide to the DTrace kernel section. So what trace does is it says, I want you to keep track of where we are in the code path. So every time I enter a subroutine, I want you to increment a level counter, and I want you to copy the name of the subroutine and store that in a buffer inside the kernel. And in this particular case, because we didn't specify otherwise, DTrace is going to output that to standard out. So as soon as this happens, it's going to go ahead and execute it, and it's going to print indented with arrows to signify whether it was an entry or a return, what the subroutine name is that was entered or returned from. And so what you'll get is a nice output with indentation and arrows showing you the actual code execution path all the way through your Python application. And that includes all of your standard library code, everything that basically isn't in C. So a huge, huge caveat with Python and DTrace, and this is really important, is that Python visibility for the software is only provided to the Python code itself. If you have libraries like, for example, simple.json, or if you use cpickle or something like that within your code base, then DTrace is not going to have visibility into that. And that's just simply because the DTrace provider that's in Python doesn't extend into compiled libraries. So that is a caveat with this particular technology. But that's what's going on here. I should say also that the copy and stir, all that means is that we're telling DTrace that arg1 is a string and that it should copy the value that's in arg1 into that kernel buffer that I mentioned before. And then finally, I wanted to talk about these command line flags because there's a whole bunch of them. They don't make any sense and they're kind of cryptic. That's guilty as charged, but if you are familiar with Unix, you know that that's a pretty common idiom in Unix, is to have all kinds of crazy arbitrary command line flags. All right, so -Q means I want you to only print information related to these specific probes. Any other kind of information you should squelch. Capital F means I want you to do that tabulation that I talked about. So I want you to increment this level counter and indent every time I have a new level of execution. And then the Z, that means usually DTrace will complain if no probes match the specification. So, for example, if you wrote a DTrace script with a probe that wasn't going to fire, then DTrace would complain about that. If you give it the the capital Z argument, what that means is I recognize and accept that if the capital Z is that may not fire. And then S is, as I mentioned before, S just says that we're going to be using these probes that follow behind the S, that they should be activated, and the metadata for those probes should be stored in the kernel. All right, so that's example one. And by the way, this is an actual script that if you cut and pasted it and executed it with a DTrace enabled Python, would show you a nice indented script. So this is an actual script that actually works. And if you want to go ahead and give it a try later, that would be great. This is an actual DTrace script that does something. So here's another example just to make this a little more clear. This is a little bit more complicated of an example. It uses associative array. So in this particular case, we have different command line flags, as you can see, and we also have 2 different probes that are firing. The first one is a function entry. So what we're trying to do here is, you can see in the comment up on the top action, that what we're going to do is count the entries by package and subname. So every time that Python enters a function, it's going to essentially join the file name, which is the first argument, and it's going to join the function name together, and they're going to be separated with a dash, and then it's going to count how many times that source file plus that function were executed. And then at the end, you can see the highlighted end block on the bottom half of the slide. We're going to throw out everything except the 10 highest. So we have this associative, we have this counter that we're calling at. There's no special name to that. You could actually have the at B, at A, at B, at cats, whatever you want to call it. It doesn't really matter. But as long as it starts with an at sign, then it will become an associative array, or it will become an aggregate variable. So what we're saying at the bottom is, I want you to truncate that, and I want you to do that at the end of my script execution. So we talked about the string join stuff. That's basically just copy these strings together. And we talked about count, which is an increment counter. So every time this thing increments, it's going to increase that value. And then we talked about the trunk. And here's a screenshot that shows what this actually does. So in this particular case, I have a unit test for a library that I wrote called PyGet, which is a client for a service called ge.tt. And this is the unit test execution, and this shows you what all the most expensive parts of executing that particular unit test are. And in this particular case, you can see that the SRE parse library gets a lot of play. In fact, the most commonly called method in the whole unit test is a library function called sreparse.py, and it's called __ next because it's part of an iterator. And then on top of that, you can see that we're using urllib and URL parse quite extensively, and that makes sense because this is a web API client, and so that's to be expected. So this is a really handy way to just easily see, okay, here's all the hot functions that are in my code. They're library code, so it's not really clear if it's going to be optimizable or not, but at least we'll give you some insight into what the most expensive parts of your program are. All right. So here are some really common aggregation functions. I mentioned that there are more than this, and that's fine. These are the ones that I use most frequently, and so they're the ones I wanted to talk about. Average does what it says on the tin. Count, we already talked about. Lquantize is a really interesting function, and then its sister function, quantize. I'm going to talk about those last because they're actually the most interesting from all these. Sum, of course, aggregates and sums everything in, pulls out the minimum, max, pulls out the maximum from those arrays. And then the quantize functions are actually really cool. This is one of the things that DTrace does super well, and why DTrace sometimes is better than a profiler. One of the things that profiling does really commonly is that it aggregates all of the runs of a particular code path into a single number. So what that means is that you typically will lose outliers. You'll have an average execution time, but if something took a really long time once or twice, you're going to lose that information. And a really common pattern to see in a lot of functions is kind of a bimodal thing, where if you have a cache hit, either from the operating system or inside of your application code, it's going to return really quickly, and later if it has to look up something from the database or go to this file, it's going to take a lot longer. And so your average is actually going to be in the middle of those two numbers. You're going to see kind of something that's after the cache value and before the actual retrieval number. And with DTrace, with the quantize functions, you actually get a histogram, built-in histogram, and then the only thing that changes between those is the base. So linear is integer 1, 2, 3, 4. Quantize is the log with powers of 2. And so what DTrace actually gives you is a histogram, and it will show you that you have a bimodal distribution, and it will tell you using those histograms exactly how many you have in each one of those quantized buckets. It's very powerful and super useful. It's actually one of the killer features of DTrace, and it's one of the reasons why that I'm enthusiastic about this technology. We've reached another transition point here. I want to talk specifically now about how to build DTrace in Python. Also, talk a little bit about how to get DTrace into your Python code if it's not already there. So are there any questions at this point in time that we haven't covered yet?
There's just one question about DTrace and Windows options.
Yeah, so unfortunately, I don't think that there's ever going to be an option for DTrace on Windows. And the reason for that is simply because the amount of engineering that would be required to do that is really high. And I think that Microsoft as a company is not been especially interested in instrumenting their code to the level that that the Solaris folks have or that Mac OS X has. So if you're running Python on Windows, then you're pretty much going to have to stick with profiling. And that's an unfortunate situation, but that's just how it is, I think. It would be really nice and handy if DTrace was available for Windows, but as I mentioned, it requires pretty extensive kernel cooperation, and I just don't know how that would really work in a Windows environment. Certainly would require Microsoft's participation, and to my knowledge, that's never been something they've seriously pursued. So sorry about that. All right, so we're going to talk about DTrace in Python now. Really what I wanted to talk about was how to build your own Python with DTrace enabled. So the easiest way to do that, at least on OS X, is if you have the Homebrew. There's a project called Homebrew, and it has this tool called brew, and it actually supports with DTrace right out of the box. You just do a brew install Python, and you stick the -- with DTrace, and it just builds it for you, puts it into user lib, and that's it. You're pretty much done at that point. I like to do my Python builds in virtual environments. And if you like to do that too, then this next slide is for you. There's a project called Pythons with a Z. It's a fork of Python Brew. Pythons is a little more maintained, I guess is the right way to put it. And I just submitted a pull request a couple of days ago to make this really simple, but the idea is that you just do a Python install, and you can do the version that you want. It has to be a 2.7 series. So you would do Python install, and then you give it the DTrace option, and it's 2.7.5, and that's it. I've been having a little bit of a back and forth with the author of Pythons. He's interested in taking the patch from the pull request, but we're trying to figure out what way to integrate it is going to be the best way for people that are interested in having a non-DTrace Python. And you'd say, well, why wouldn't you want a DTrace Python? I don't really know, but I do know that there are people that would want to have no third-party patches to their Python. And if someone is like that, if it's really important, then there has to be a way to do that with no patches. So anyway, if you check out my fork of this Pythons project, or you go to the URL that's in this slide, and you pull down that patch and apply it to your the Python code base, then you'll be able to do it like this: Python install --DTrace, and then some version. 2.7.5 is the most recent 2.7 version. And another question I get pretty frequently from Python folks is, why doesn't Python have DTrace functionality out of the box? And I don't really have a good answer for that, to be honest with you. There's a bug that's been open in Python for a very long time, I think since 2010, that really kind of has centralized all of the DTrace support requests for Python in it. Unfortunately, the Python core team has decided that they didn't really want to deal with it for the 2 series. And the 3 series, it's still sort of an open question whether or not it's going to get integrated in there or not. I would love to see it get integrated into the 3 series, but as far as I know, it's really not something that's available right now. The next thing I wanted to show you was how to tell whether or not you have a DTrace-enabled Python. It may not always be super obvious, but in the patched version that I support or that I have recommended, there's actually a DTrace module, and it has a single attribute inside of it. So if you import DTrace and you don't get an import error, you can actually make DTrace.available, and it should return a true value, and that will show definitively that you have a Python that supports DTrace. So that's a good way to tell programmatically if the code that you're running supports DTrace or not. You can check for import DTrace, import error, and then if you don't get one, you can actually say DTrace.available if it's true. So the next thing I wanted to cover in the talk was the different functions that are the different probes that are available with Python. Let's talk about the first. We've already seen these, a couple of them. The function entry and function return ones we've talked about quite a bit. So the way that these slides work is that the top part of the slide, function entry, function return, and line, those are the probe names. And then at the bottom of this in parentheses are the different pieces of metadata that these things provide. So arg0 in this case is the file name, that's the source file. arg1 is the function name, and arg2 is the line number. So that would tell you, that's the line that the interpreter sees it, not necessarily the line as it shows up in your editor. So the line probe actually fires every time the interpreter advances a line. So if you wanted to do line-by-line probing, you could actually do that. You say, well, why is that useful to me? Why do I care about that? It's possible that you would be in a situation where you want to trace only from line 42 to line 47 in a particular script, for example. And having a probe named line lets you do that. So you could say, for example, I want to fire this probe. I want to track the line number, and I only want to execute the action if the line number equals 42 to 47. So you could totally do that in a D script, and this would let you probe a very, very specific part of your code base without touching any of the other parts of it. So that's a really useful probe to have. But I will also admit that the most common ones that I use myself are function entry and function return. And I suspect that will be true for the vast majority of people. But we've already talked about this. So people ask, why do they have this line probe? That's why they have it. The next one is the GC start. So when Python starts its garbage collection cycle, you can fire a probe. The metadata that it returns in arg0 is a generation. That's the integer value. And it's similar to the information that's provided if you were to, say, make a call to gc.collect in the Python interpreter. It would tell you that same amount of information. You're probably not surprised to know that there's also a probe that will fire when garbage collection is finished. And it provides a objects collected piece of metadata that also is an integer. And it tells you how many objects Python decided to destroy or dispose of. The next one deals with instances. So we have two at the top. We have instance new start and instance new done. That will fire every time a class is instantiated, and it will fire every time a class is finished being instantiated. And then at the bottom, you have instance delete start and instance delete done. That's the inverse of the top. Every time a class is garbage collected or explicitly deleted, it'll call these two events will fire if these probes will be invoked. The metadata that's available here is a class name and the file name. And the file name in this case is the source file name, just to be super explicit about that. It's fully qualified with the path name. So, those are all the probes that are available. We have function entry, function return, line, garbage collection start, garbage collection done, and then all of the instances as they get created and get destroyed. So those are the basic probes that are available to you. One really neat thing that is pretty recent is this. You can actually create your own Python probes using DTrace written in Python by checking out this particular project on GitHub, Python DTrace. It's also on PyPy, and you can just pip install this if you like. The documentation for it is a little rough right now. It's not super well documented, but what it enables you to do is for example, essentially create probes that you can call from your code and then in your dscripts without writing any additional instrumentation. Say, whenever my user space probe fires, take this action or profile this function, or tell me how many sockets get created, or tell me how many database handles are open in this state, all sorts of stuff like that. So it's really kind of neat, and if this is something that interests you, I would highly recommend that you check out this project. It's pretty interesting. So here's the DTrace resources that I talked about. DTrace has a lot of information that's available online. It includes the first link here is actually a really great resource if you're interested in DTrace and don't have a lot of experience with it. Oracle, for one of their conferences, published this hands-on lab. So they have this DTrace HOL that stands for handsonlab.com, and it actually has, I think, about 12 or 13 hands-on exercises, and there's a virtual box that you can download of Oracle 11 that has like all of these different exercises that you can actually just run inside that virtual box. And it's a great way to get familiar with the whole DTrace stack from start to finish, all the way from kernel level calls to system libraries to application code. There's a couple exercises that deal with Java, and there's a couple that deal with PHP on Oracle Solaris 11. And so it's actually kind of a neat resource for everyone to take advantage of. As I said, it's just available for free. There's no cost or anything like that. You can just download the virtual box and go ahead and start using it and playing with DTrace right away. If you're interested in doing DTrace work, that's a really cheap and fast way to get started with DTrace as a technology. The second resource, there's a great website which is maintained by the authors of DTrace called dtrace.org. It has quite a bit of documentation and also a lot of really interesting and useful DTrace scripts. So I mentioned that DTrace has this D scripting language. There are a lot of prefabricated D scripts that you can just go out on the internet, find them, use them, and it's great. The third link is actually there's a book that was published a couple years ago, and it's really, really thick. It's probably the most comprehensive DTrace resource that's available. It has a website called dtracebook.com, and there's a whole chapter in there devoted to how DTrace interacts with like 10 different programming languages, including Python. There's a number of pre-canned DTrace scripts that you would find useful, and so that's a great resource. And then finally, if you're interested in that book, the link to find it is that bottom one there. And it is very, very thick and very large, but it is a very comprehensive resource as well. I also promised that I was going to look up that kernel module since that's a question. I'm going to go ahead and do that. So if there's any other questions from the audience, I would love to take care of those or hear what people think.
All right, people. If you'd like to send in a question for Mark, just preface them with a Q. Otherwise, we just had one that came in from Twitter. Do I need to know the internals of kernel to use DTrace?
No, you don't. Actually, if you only care about application level code, the only thing you need to be familiar with is the D scripting language. And kind of what I talked about today is definitely enough to get started with. And then what probes are provided by the particular application language. In this case, that would be Python, and we talked about all the different ones that are available there. And don't really need to know anything about how the kernel works or how DTrace itself does the things that it does. You just have to know, how what the probes are that are available and how to connect them together with D. And like I said, there's a lot of pre-canned scripts, including the ones I talked about today in my talk, and then all those other resources that I just kind of covered. So hopefully that answers that question. There it is. Okay.
Great.
So if I publish this in the chat window, will other people see it, or how does that work?
We can distribute it for you.
Okay. Cool. I'm going to go ahead and paste it in here. But basically, the net is that if you use your favorite search engine and you type in DTrace, the number 4 in Linux, it should be on the top 10 hits there. And it's on GitHub. So if you also want to search from it on github.com, that would be a good place to start. So that would be a good resource for people that want to play with DTrace on Linux itself. Are there any other questions or anything else that people want to know about DTrace and Python?
Looks like that's it for questions. Is there anything else you'd like to say before we finish up?
There actually was one thing that I promised that we were going to do, and for whatever reason it just didn't work out. I wanted to do a live demo. In my talks, when I do them at OSCON, there will be a slide that talks about my perilous live demo. I was going to do a live demo today, but I think the screen share functionality didn't work. And so what I decided to do is within the next week, I will put together some kind of screencast that shows me doing DTrace on Python, and I'll post that on YouTube or something and make it available to people. So if you expected me to do some live demos today, I'm sorry to disappoint you. But I promise that we will have a live demonstration of how this works pretty soon.
Mark, it looks like another question came in.
Okay.
Do the different app languages support DTrace differently, like Ruby, for example?
That's a great question, actually. The thing that is different between all the different languages is the probe names and the metadata that those probes give you. Speaking from the perspective of Perl, which is another language that I know quite well, the DTrace probe names are different, but they actually provide the same amount of information. In Perl's case, they have a probe called subentry and subreturn, which is exactly like Python's function entry, function return. It's just that the metadata that they give is different and the names of the probes are different. But other than that, they're exactly the same. One of the key things that the DTrace the DTrace authors wanted to give was a generalized framework, so that if you learned how to use DTrace, you really would be able to do a lot of tracing without having to understand how it's all implemented. The only things you would really need to know is how to wire them together in the D scripting language, and then how to manipulate the metadata that the probes offer. Great question. Thank you for asking it.
All right. So if that's all we have for today, then I'd like to thank you for your time and a great presentation. And just as a reminder to everybody, we will have the archive of this webcast up within 48 hours. So thank you all for joining us today. We hope that you had a good time. I know we did, and that we'll see you in future webcasts. Also, you can see Mark live or in person at OSCON at our flagship conference in July. So a big thank you to Mark for presenting to us today. And that is it. Goodbye.
Okay. Thank you. Goodbye.